Hello everyone, welcome to a short video on solving a LeetCode problem with APL. Today we'll be taking a look at, let's sort this by difficulty to make sure I start with the easy ones. So today we are going to take a look at problem 1512, number of good pairs. And that's because I already solved 1470 in APL, I just didn't submit a solution in Python. Or in any other language for that matter. So number of good pairs. So we are given an array of integers, and we say we have a good pair ij if the numbers in those two positions are the same and I is smaller than j. And now we want to return the number of good pairs. Okay, this is actually fairly easy to do. Amazing. Well, fairly easy to do in APL. If I were to do this in some other language, it would still be easy, but it would be a different approach. So let's take an example input. Let's copy this and let's paste it in here. This is the vector we are going to be playing with. Now the first thing we are going to do is to use an outer product to compare all of the numbers with themselves. So let's do, this is the outer product, and it compares it's going to take the equals, and apply the equals to all of the combinations of arguments on the left and right. And this means that this 1 was compared to the 4, the 5, and the 6, and that gives 0, 0, 0, because all of these are different. Maybe it would be smarter if I were to do the following: 10, 100, and 1000, and instead of equals, let's put there a plus. Now this is 1 plus these three numbers gives me the first row, 2 plus these three numbers gives me the second row, and 3 plus these three numbers gives me the third row. So this is outer product. It takes a function over there and applies the function to all of the combinations of elements on the left and right. So what we're going to do is take the outer product and compare V with itself, and we get a matrix with 1s in the diagonal because every element is equal to itself. And then we have these 1s over here. And now what we can do is we can either try to turn half of these 1s off, because we don't care about the different yj combinations, we want only unique pairings, and also we don't care about the diagonal. But the other thing we can do is we know exactly how many 1s are in excess, so we can actually sum all of these up. And the way we do that is by first reveling, that is taking the matrix and building a vector with all the rows, then summing everything together. And then what we can do is subtract the number of elements in V, because that's the number of elements in the diagonal. Oops, what did I do wrong? Sorry, that's not what I meant to type. I meant to compute the elements in V and then subtract those from the count, and then divide by 2, because we are counting each pair twice. So we can divide by 2. And this is take 2 and divide what's on the right by that. So this is our short solution. This is fairly short. Yeah, well, there's a repeated V in here, so what we can actually do is say that this function takes as arguments V and itself on the left, and then there we go. And so let's save this as a diffn to test with the other sample test cases that they provide. So let's see. Whoops, I missed the commute operator there. So the solution in our first example works fine. This should give 6. So let's see. 1, 1, 1, 1. And this should give 0 because all numbers are different. Okay, good. So this is it. Now, is there something else we could do? Because I'm looking at this matrix and let's see if there's a very clever way to erase half of these. Well, what we can actually do is, so we can take that matrix that compares all of the numbers with itself, and now we can also build a matrix that's all ones, for example, in the strictly upper half of the matrix. And by half I mean separated by the diagonal. And the way we can do that is by actually doing something similar with the outer product, but now doing the outer product with less and selfie on iota the number of elements of V. So iota tally V gives me, let me show it to you. So iota tally V gives me the first non-negative integers as given by as set by the size of V. So we have this, and now we can multiply this with this original matrix. So we can take that and multiply it, and now we can sum the revel. So that's the same thing, and it seems to me that this is easier to write in a tacit form. So what we are going to do is, this pattern over here, we are trying to apply, this is more or less like a fork. So there's the left tine and then the multiplication, and then the right tine. So let's do this as the left tine, and then the middle function of the fork, and then the right tine should be all of this. So this gives me the mask, and then in the end I just sum the revel. And there's a lot of dots in here, but this is actually quite elegant. I find it quite elegant. There's some interesting faces in here. So this is the nose of someone. And there's also another nose in here, and maybe this person over here is winking. I don't know. Yeah, but that's it. Sorry, I digress. These are two fairly simple solutions. I think the tacit one is maybe not as easy to digest, but feel free to work through it and then ask any questions you might have in the comments. And remember that you can submit your own solutions to the GitHub repo that's hosting all of this code, and you can find a link in the description. And other than that, I will see you in the next video. Bye.